This week we're going to talk about slopes and get an introduction to slope staking. So you're familiar with slope from math class, where slope was expressed as the variable m, and it was equal to the rise over run, or the rise being the change in value across the y-axis dimension, and the run was the change in value on the x-axis dimension. This is a bird's eye view perspective, or a plan view perspective, and we're going to talk now with regards to slope from kind of a construction, surveying, excavation point of view. So this is a profile view, and the equation's the same. Slope is still rise over run, but now the rise is going to be a change in elevation, and the run is going to be a horizontal excuse me, a horizontal distance expression. So we can express slope two different ways, both as a percentage and as a ratio. In a percentage, obviously the units are percent, and what that means is we're expressing a slope in terms of what is its elevation change for every 100 horizontal feet. As a ratio, we're going to express slope h to v, horizontal to vertical ratio. And the vertical is always 1, and the horizontal is the horizontal distance required to achieve 1 unit or 1 foot of vertical change. So if we look at slope as a percentage, it's calculated just the same as m in math class. If you had a 20-foot horizontal distance change and a 2.4-foot vertical change proceeding left to right, you have 2.4 divided by 20 equals 0.12 times 100, obviously, to get it into a percentage, or 12% slope. That's how we would express that. And slopes and angles, they're all proportional to one another. So a 12% slope, regardless of what your horizontal distance is spanning, just means that if you extended that triangle out proportionally so that you had a 100-foot run, you would be gaining 12 feet of vertical elevation change. Pay attention to your signs, pay attention to your direction. You obviously can have negative slopes as well. So if we were going right to left in this example, our change in elevation is now negative 2,059 feet. Your horizontal run is 7,900 feet for a negative 0.26 or a negative 26% slope. And one of the things we think about especially for like road design, is how do you work with slope, say, limits? Say you have a maximum slope that you're not allowed to exceed. On interstates, you often see warning signs whenever the slope goes over 8%. That starts to get pretty taxing on downhill braking for tractor trailers. Trying to climb something over 6 to 8% going uphill, you're basically putting four-way blinkers on if you're a tractor trailer as well. So interstates rarely exceed 10% other than in unavoidable circumstances. So if you have these slope limits that you have to stay within, how do you stay within them? You have a fixed elevation that you need to achieve. You're going up and over the East Ridge, going from Butte into Whitehall. You can't change the elevation of the East Ridge. You have to achieve that climb. So if you can't exceed 6 to 8% in slope, you change your horizontal distance, right? You achieve the same amount of elevation over a longer horizontal distance, and you've decreased your slope. And that's kind of one of the fundamental design concepts you keep in mind when you're designing alignments is how much run, right? How much horizontal road do I need to find room for to gain whatever vertical change it is that I'm needing to accomplish. This is exhibited really well in switchbacks. And if you're a cycling fan, most people aren't in this country, but I've always really liked pro cycling. The Alpe d'Huez mountain in France is one of the classic climbs. It uses 21 switchbacks to ascend the mountain, and essentially they're doing that so they can extend the length of the road to achieve the fixed elevation. There are slopes along this road that exceed 22% on some of those switchbacks, which is just incredibly steep. You and I would not be able to bike it on a bike without pushing, but you know, pro cyclists, they can make it. A little more local here, we do the exact same thing down there by Red Lodge on the Beartooth Highway, right? You can see on that left picture those nice, consistent, kind of gradual slopes going back and forth up the mountain. And I don't know what that slope is. I'm guessing it's probably a consistent 6 to 8% slope going from the bottom of the valley up to the top of that mountain. Here's just a question. It's not a trick question, but can a slope exceed 100%? And I'll give you a second just to think about that, or pause the video here if you want. The answer is yes, of course it can. Slope is just right, rise over run. And if you're changing more than 100 feet in elevation over a 100-foot distance, well then obviously you're going to have a slope steeper than 100%. So when you're working calculations, always use the common sense rule of thumb, right? At the end of when you've calculated a result, ask yourself, does my answer make sense? But don't let a really, really high slope number automatically make you think you did something wrong. Just like when we talked about water content in soils, you know, and I asked you that question, can a soil have a water content that exceeds 100%? And it absolutely can. Clays often double their weight in water, and they can have water contents of 200%. So same with slopes. This is the other way of expressing a slope. This is probably how we're going to use the context of our discussion in slopes here these next couple weeks. We're going to refer to slopes as ratios. So when you're referring to a slope by ratio, you always want to express the horizontal change to the vertical change, h to v. And v is always 1, right? We want to keep this simple. We want to make the math easy for ourselves. So example ratios are 1 to 1, 3 to 1, or even 1/2 to 1, right? Your first number, your horizontal value, doesn't have to be larger than your vertical expression. So if we look at these examples, a 1-to-1 slope obviously has the same amount of rise for the same amount of run. A 3-to-1 slope is flatter, right? You're achieving that same 1-foot vertical rise, but now you're spanning 3 horizontal feet. And a 1/2 to 1 ratio is a steeper slope, right? You're achieving 1 foot of vertical and only traveling a 1/2 foot horizontal. So that's pretty rare to have those steep slopes in construction. The ratio or the steepness of the slope we're dealing with in construction on soils is typically dependent on the stability of the soil. And once you get over 1 to 1, soil becomes not too safe, not too stable. So 1 to 1, 2 to 1, 3 to 1, those are the typical slope values that we're going to use. So what's really nice about the ratio is that you can easily calculate changes in elevation or horizontal distances based on surveying measurements, right? Real common survey measurements that we go and get out there. This is just a kind of a real simple example of the natural ground and a proposed foundation wall down to a footing. And if we know, based on the design, that the bottom of the footing has to be 990 feet and our ground elevation is 1,002 feet, we know we have a cut, right, of 12 feet. That's a cut dimension. So if our soil type is requiring us to lay that slope back at a 2-to-1, right, to avoid cave-ins or unstable conditions, what's the horizontal distance that is required to achieve a 12-foot depth at a 2-to-1 slope? Well, you're simply taking your cut dimension times your slope, or 12 feet times 2, to get 24 horizontal feet. Real simple math, and this is what's critical when we get into slope staking, is this fundamental concept that distance equals cut times slope, or fill times slope if we're filling a hill above the natural ground as opposed to cutting down into the natural ground. So just a real quick review on cut and fill sections. Right, cut sections are when we're modifying the existing ground to some sort of design feature that requires material to be excavated and removed out of the ground. Conversely, fill sections are when we're importing material and building up higher than the natural ground. And just a real kind of a note on why it shows these colors here, green for cuts and red for fills. You know, we in our minds we attribute kind of positive values to green and negative values to red. And when you're computing cuts and fills for earthwork, generally you want your cuts to be expressed as positive values and your fills to be expressed as negative values. And that comes from estimating procedures, where when you're estimating earthwork on a job site, and we'll be doing this here in a couple weeks, right? When you're estimating how much earth needs to be excavated out and moved around and maybe placed into a fill scenario, well, every time you excavate a cubic yard of ground, you have material available, right? You've made a deposit into your earthwork account, and you can go spend that somewhere else on the job site. So cut means you're gaining material in your account, and fill means you're having to spend material from your account. So that's why we give cuts a positive designation and fills a negative designation, just like a bank account almost. So typically you don't always have a 100% cut scenario or a 100% fill scenario. You know, engineers will try to balance their design along the natural topography so that you can excavate cut out of the ground, like here, and just lay it over and deposit it down there where it's required in the fill scenario. You know, if you don't have to spend a lot of time and money moving ground off-site or transporting it to far away locations of a roadway job site, you're saving construction time and cost. So you try and balance things based on expansion and compaction rates of the soil. So basically you're playing with this design elevation. Where do you want that roadway to be such that your cuts will balance with your fills? A typical cut slope can be steeper than a typical fill slope, right? You might see a 1-to-1 on a cut, or a 2-to-1, even a 3-to-1, a nice flatter, gradual fill slope. And that's because you need that fill slope to be safer if a vehicle rolls its tires off the traveled roadway and catches that. You want a recoverable slope, right? If that fill slope, if that red line is too steep and tires come off the pavement and hit that slope, they're going to grab those tires and roll that car. So 3 to 1, even 4 to 1 on a high speed roadway are more typical, just to have that recoverability. It's a safety factor. So slope staking, we're just going to kind of get into the general equation and the excuse me, the general process of slope staking this week, and then next week we'll focus more on some examples and the calculations. But the definition: slope staking is the process of intersecting a geometric figure with a surface that has no equation. And it sounds a lot more complicated and voodoo than it really is, right? Your geometric figure is your cut or your fill slope, right? It's the design feature. It's what do you want the natural ground to be modified to reflect. It might be an excavation for a building. It might be a roadway design. And the surface that has no equation, well, that's the natural ground. So if you think about your design feature, it's designed. It's maybe flat, maybe has a crown, and then it has a predetermined slope based on soil conditions. That's designed. That has an equation. We know exactly where that exists in the world. Your natural ground is random. It undulates, it goes up, it goes down. It has no equation that we can follow. So we don't know how those two surfaces are going to intersect one another. Think about to geometry when you learned about the equation for a line, right? A line equaled y equals mx plus b, right? That's the equation of a line. And if you set two lines equal to one another, when their y values and when their x values equal one another, that means those two lines have intersected and crossed themselves. Or not crossed themselves, crossed each other. And that's an intersection point. We don't know the y equals mx plus b equation for the natural ground. It's unknown. It's out there. So we have to go through a process called slope staking to figure out where a line with an equation is going to intersect a surface that has no equation. And it's an iterative process, which means it's trial and error. You try something, you solve for it. If it doesn't equate, you try it again and you get a little closer. So just a little bit of definition here in slope staking. Typically, everybody calls these points catch points. But catch points truly only apply to fill scenarios where your modified elevated surface comes down and catches the existing ground. When you're excavating and removing material and bringing those slopes up from a design surface to intersect the natural ground, those would be called daylight points. It's where your design surface is daylighting and finding the ground. But you're going to hear me, you're going to hear everybody just call them all catch points. Where does your design catch your existing? So this is a scenario that kind of illustrates the variables that we need to go over when we start slope stake calculations. You can see the natural ground that we have here. I have a pretty typical design elevation and a design cross-section. We have a centerline hub, so we're assuming some sort of construction staking has occurred and centerline points for this proposed road have been established in the ground. We'll go to the general equation, I guess. The general equation for slope staking is x equals L plus slope times cut fill, where those variables are shown in the diagram here. X is the horizontal distance from your center line or your control point out to the horizontal distance from the center line out to the end of the designed line, or where your catch point will be. L is the design distance from your center line out to the point that I'm going to call the hinge. Right? And the hinge is where your slope begins. L is fixed. L is a fixed dimension. It doesn't change. From that hinge point, that's when we go up on a predetermined calculated slope. Could be 1 to 1, 2 to 1, or 3 to 1. And we don't know how far we're going to have to run that slope out horizontally before we catch the ground, right? Because the ground is an unknown surface equation. So that's a variable distance. L is a fixed distance. This horizontal component of our slope is a variable unknown distance. We have to solve for that. Come back here to our variables. Slope is the designated slope of that surface. If we're designing a 2 to 1 slope, we use the number 2 in our equation. If we're doing a 3 to 1 slope, we use the number 3. And obviously, 4 to 1 slope, you see where this is going, we use the number 4 in our equation. And then CF stands for cut fill. Cut fill is the vertical distance from the hinge point up to the natural ground. And then you see up here what I have labeled is a measured guess. That's where we come into play. This is the iteration process here. Right? We don't have this green line existing out there in the real world for us to look at and help us know where to begin cutting. All we have is a natural ground surface and a center line point. And we have to walk out here, generally with a tape measure, that's close enough, and we have to guess how far out do we think we need to be to begin cutting on this slope so that we achieve the design elevation at the hinge point. And then we have the design L distance back. So that measured guess is the essence of slope staking. How far out do you have to be? If we look at the process for slope staking, it's a pretty simple process, and once you do it 1 or 2 times, it really becomes almost automatic that you can do in your mind. But until you really get that clear comprehension of it, it can be really confusing for people. But step 1 is to take that measurement guess, or take that guessed distance and measure it along the natural ground. Step 2 is you need to know now what's the elevation of your natural ground at the point that you're guessing, right? Because you don't have the equation of the ground, so you don't know what the elevation of it is without measuring that. So you can measure elevation in any manner of ways. You could use a GPS. Most people use an auto level. You can also use a hand level when you're slope staking. Slope staking is not high precision work. If you're getting plus or minus a foot, plus or minus a half a foot, you're generally more than close enough for this kind of rough excavation work. Once you know the elevation of the ground where you took that guess, now you can compute the cut fill, because the cut fill is just elevation of the ground minus the design elevation at that hinge point. If you know cut fill, you can now compute the horizontal distance required to achieve that cut fill along the prescribed slope, and then you add that to L. That's where the equation comes from. Slope times cut fill is the variable distance. You add that to L to get X. If your computed value for X is within 1/10 of a foot of what you initially guessed, you found your catch point, and you stick a stake there in the ground. More than likely it's not equal. More than likely your X was longer than your measured guess. If that's the case, you have to re-guess, measure out further, and repeat the process. If X computed to be shorter than what you measured your guess to be, you have to move in, repeat the process. And if they were equal to one another, or typically within 1/10 of a foot, you found your catch point. So where this becomes a challenge is when the natural ground doesn't stay the same elevation for you. If you're on a side hill and that ground elevation is changing as you go further away or come further in, that's when the excuse me, that's when the iteration process takes 2, 3, maybe even 4 tries to find that catch point. You end up chasing yourself uphill or downhill. But that's the process. We'll get into kind of specific examples with some numbers and calculations next week, and then we'll also perform slope staking off of those centerline points that we established up in Thompson Park last week.